These are the examples that go with lesson 3.2, measures of spread. Example 1. The table shows the average temperatures in St. Louis for a certain year. Compute the variance. Compare to the variance in temperatures for San Francisco, which is 14.083. Okay, let's go back for a minute so we can figure out what it is we need to find the variance. We're going to need to know the mean of our population. We have our data set already. That was all in the table. And then we're going to divide this by the number of items in our table. And I think there's 12 since it's for a complete year. So there's 12 months. All right. So what this means right here is we're going to take the mean and we're going to subtract it from each separate data point in the table. And then we're going to square it. And the purpose of squaring it is to make all of our numbers positive. And once we've done that for every data point, then we're going to add all those squares together, and then we're going to divide it by n. Now, I like to separate mine out into a chart. And so what I'm going to do is we'll come back over here. We're going to get the data. And the first thing we want to do is figure out what the mean is. Okay. The symbol for mean is this mu. And remember, this just means we add all the data points up and then we divide by the number that there are. All right, so let's get this from the calculator. And I am getting 673 from adding all of those together. And there were 12 data points in the table. We're going to divide this by 12. All right, let's divide that in the calculator. And this is giving me 56.083. And then that 3 is repeating there. Okay. All right, so we figured out what our mean is. Now I have to take each data point from the chart and I need to subtract the mean from it. Okay, so as you can see, I've got my chart set up here, and underneath X I have all of the temperatures from the table in our preceding slide here. And my next column here, I'm going to take each one of these individually and I'm going to subtract the mean, and then I'm going to write that answer right here in the second column. Okay, so in column 2 you can see I have actually subtracted my mean from each of my data points, and I rounded off to 3 decimal places here. Okay, in column 3, I'm going to take all of my numbers in column 2 and I'm going to square them. And I'm going to square them because I noticed that this one right here is negative, so is the one underneath it, so is the one underneath it, and then I have 2 negatives down here at the bottom. If we go ahead and added this column together, we would find out that this column would be equal to 0, and that's not going to be our variance there. So we're going to square it, and then we're going to add all of those together, the sum of those squares. All right, so let's do that. Okay, and now you can see in column 3 right here, I have actually taken column 2 and I have squared each one of those numbers and I've written them over here in column 3, again rounding everything off to 3 decimal places. All right, the next thing we want to do is we want to add this column together, and we're going to get a grand total down here for all of the sums of the squares. All right, and my sum that I'm getting is 3,502.918. All right, and now to find the variance, we just need to divide by n. Well, remember, n is equal to 12 because 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. There are 12 data points. Therefore, our variance, which is the little sigma squared, is equal to the sum of our squares divided by 12. And if we put an approximation in here, we're going to get 219.910. So there is our variance. Now we are supposed to compare that 219.910 to the variance in the temperatures for San Francisco, which is 14.083. So this is the variance for San Francisco. And considering that St. Louis has such a high variance, it looks like the temperatures in St. Louis are going to vary a lot more than the temperatures in San Francisco. All right, so here's our conclusion. The temps in St. Louis vary more than those in San Francisco. And we would probably expect the range of temperatures in St. Louis to be much larger than the range of the temperatures in San Francisco. And that could account for why the variance is so large. Okay, example 2. Find the sample variance and the sample standard deviation for the following data sets. And we have two data sets there, part A and part B. Now remember the difference between the sample variance and the population variance. For the sample variance, we're dividing by n-1 or 1 less than our sample size. And for the population variance, we are dividing by n for the sample size. Okay, so let's go ahead and figure out the mean for both of these samples and the n-1. All right, for part A, when we add all of those data points together, you get 20. And there are 1, 2, 3, 4, 5, 6, 7. There are 8 of them. So we're going to divide by 8. Remember, we don't divide by n-1 until we go to find the variance there. And this is going to give me 2.5. Which means that our n-1 is going to be 7. So to find the variance, we're going to be dividing by 7 rather than dividing by 8. All right, let's figure out part B. All right, so for part B, the mean is going to be 212 divided by 6, and this is going to give me 35.3, and that 3 is repeating there. And I'm just going to leave it rounded to 1 decimal because part A was rounded to 1 decimal. Our n-1, this is going to be 6 minus 1, which is going to give me 5. And I don't know if you caught this, but I need to change my notation here because that is the notation for standard deviation. And what I should have here is x bar. That is the mean for our sample. Okay, let's go over to the next slide. All right, we know that in part A, we had the mean to be 2.5 and n-1 was going to be 7. And we got to put all these data points in here. So let's see, we got 2215, 2215, 4501. Okay, so we are going to find the variance just like we did in example 1, and then to get to the standard deviation, all we need to do is square root our answer. In this column, I'm going to take each of my data points and I'm going to subtract that mean that we just found with 2.5. And then in the next column, I'm going to square all of those. Okay, in column 2, now I have subtracted all of my data points minus the mean. Here they all are. In column 3, I'm going to take everything I have here in column 2 and I am going to square it. All right, and now I have filled in column 3. This is each one of my differences over here raised to the second power. And then remember, to get to the variance, we're going to have to add this column together. And that sum is going to give me 26. The variance for our sample here is going to be the sum of those squares divided by our n-1, so 26 divided by 7. And this is giving me 3.714. And now to find the standard deviation, I am going to square root that number, the 3.714. So this square root is compensating for the fact that we squared this entire column right here so that we could have positive numbers. All right, so let's see. The square root of 26 divided by 7 is 1.927. All right, so the standard deviation for our data set is almost 2. Okay, you can see I have transferred over the things that we found for part B. We've got the mean for the sample to be 35.3, and we said n minus 1 was going to be 5. I've gone ahead and filled in all my data here in this first column, and then in column 2 now, remember we're supposed to subtract each one of these minus the mean. Alright, so I've filled in column 2 right here and subtracted each of my data points minus the mean. Now in column 3, we are going to take everything that's over here in column 2 and we are going to raise it to the second power. Alright, and now that we have squared all of our differences, we're going to add this column together and then we're going to divide it by n minus 1 or 5, and that's going to give us our sample variance. Alright, and I have added all my squares together and my total is 1,409.34. The variance, or S squared, is going to be the sum of those squares divided by our n minus 1 value up here, which was 5. And this is going to give me 281.87. And then to find the standard deviation for our data set, we are going to square root that number, 281.87. And that is going to give us 16.79. And there's the standard deviation for our data set in part B. And there is our variance. Example 3. Find the population variance and the population standard deviation for the data set 7325493. Alright, we need to know what the mean is for our population. And it is a population, so this time we're going to be dividing by n instead of dividing by n minus 1. Let's see, n is equal to 1, 2, 3, 4, 5, 6, 7, 8. Alright. Alright, let's add all these numbers together. And my calculator is telling me that's going to give me 39. And we're going to divide this by 8. And I am getting 4.875. 4.875. Alright, let's see. Our data points here, we've got 7, 3, 2, 5, 4, 9, 6, and 3. It's going to be a little bit crammed here, but I think we can do it. Column 2, we're going to take each data point and subtract off that mean. Column 2 is completed. We have subtracted each one of the data points minus the mean for our data set here. Column 3, we are going to square all of those differences. Now that we have gotten the squares of all of our differences here, remember we're supposed to add this column together, and I'm running out of room, so I'm just going to go ahead and put my variance over here. We'll find our total, and then we're going to divide it by 8. Alright, and you can see my total here, 38.878. We're supposed to divide this by n, which we said was 8. This is going to give me 4.860 for our variance, and then for our standard deviation, we are going to square root that number. And this is going to give me 2.204. And there is our population standard deviation. And this one is the variance. Example 4, a data set has a mean of 20 and a standard deviation of 3. A histogram is shown. Is it appropriate to use the empirical formula to approximate the proportion of data between 14 and 26? If so, find the approximation, and if not, explain why not. Well, if we're going to use the empirical formula, we need to be able to see that our data is approximately symmetric. And what that means is our highest point is going to be in the middle, and the rest of the data is going to kind of taper off to the right and taper off to the left. And right here, and a good way to view this is if we put in our midpoints here on these histograms, and then we connected the dots, we would have something looking like this. So it's not perfectly symmetric, but remember, we're trying to match that pretty bell curve right here like that, and this is pretty daggone close. So I would say that yes, it is appropriate. And since it is appropriate to estimate the proportion of data between 14 and 26, that means we can use our 68, 95, 99.7 rule. The mean is located right here in the middle. 22 is +1 standard deviation, 18 is -1 standard deviation, 16 is -2 standard deviations, and 24 is +2 standard deviations. So the percent or proportion of data that is 2 standard deviations away from the mean is about 95%, or if you want to do the decimal portion, 0.95. Example 5, a data set has a mean of 50 and a standard deviation of 8. A histogram is shown. Is it appropriate to use the empirical formula to approximate the proportion of data between 42 and 58? If so, find the approximation. If not, explain why not. All right, let's again put those midpoints in there for each of these. Now remember, approximately symmetric is going to draw something that looks like this right here. Let's connect these midpoints here. And we can see our data does not top out up here in the middle and everything. It's actually dropping off to the right here. So it is not appropriate to use the empirical rule here. And the reason it's not appropriate is because our data is skewed to the right. Example 6 and example 7 have to do with Chebyshev's inequality, which we'll be covering next week in class. So we'll skip those till then and jump ahead to example 8. The lengths of newborn babies have a mean of 20.1 inches with a standard deviation of 1.9 inches. Find the coefficient of variation of newborn lengths. All right, our formula for the coefficient of variation is the standard deviation divided by the mean. In this case, our standard deviation they gave us to be 1.9, And the mean they gave us to be 20.1. And we do the division in the calculator here. We're going to get 0.095. And there's our coefficient variation.